contributions to loop quantum gravity and also for the breadth of his interest to other topics, and this was exemplified by his beautiful talk last night at the dinner. And the connection to Jurek, yes, it must go to the very early 90s.
Right, so I met Jurek when he came to the US in 1991 in Syracuse, and I heard one has to tell a story how tall Jurek is. So in 1992, the GR meeting in Argentina, I was one of the local organizers, and I got a call. I mean, the accommodations there were rather Spartan. It was a trade union hotel. And I got a call from the manager saying there's someone complaining the bed is too short. And so it was Jurek, of course. And the manager had offered the accommodation of placing two beds next to each other, which of course solves the problem of width, but not the problem of length, right? So in the end, the accommodation that was found was to get a bed with no headboards, so Jurek's feet could sort of dangle at the end. And that's how that problem was addressed. Okay, so I'll tell you a little bit about work we've been doing over the last few years with a bunch of people, Rodolfo Gambini, with whom I've been collaborating for close to 30 years, and people in Uruguay, Miguel Campiglia and Rodrigo Ieralde, and also Javier Olmedo, who is now a postdoc at LSU. This is the plan. We'll talk a little bit about how to do loop quantum gravity and spherical symmetry. And we have actually solved that problem. And then we'll do some applications, which is to put quantum fields to live on the quantum space-time and discuss Hawking radiation, the Casimir effects, self-gravitating shells, and we're now venturing beyond spherical symmetry into axial symmetry. So if you want a summary of what we've done, we have found in closed form the space of physical states corresponding to spherically symmetric vacuum spacetimes and loop quantum gravity. So essentially it's like the quantum version of the Schwarzschild solution. The exact solution in spherical symmetry with time independence. And we study quantization of test fields on those quantum spacetimes. This is something that Jurek actually pioneered in the context of cosmology, which is to study quantum field theory not on curved spacetimes, but quantum field theory in a quantum spacetime. And the main message is that the quantum background acts as a lattice regularization, regulates the fields naturally, eliminates infinities, but otherwise changes only very little the traditional picture of quantum field theory in curved spacetime. So going to spherically symmetric loop quantum gravity, the first to look into this were actually Thomas Thiemann in his thesis with Kastrup in the mid-90s. At the time, we had only the complex Ashtekar variables. More modern treatment with the real Ashtekar-Barbero variables was done by Boyowald and Swiderski. And roughly speaking, one has a triad in the radial direction and one in the transverse direction, in the phi direction, and the canonically conjugate momentum. So one has four canonically conjugated variables. And if you want to understand their meaning in terms of the traditional variables, here's the translation back to sort of the metric variables. And one builds spin network states by considering sort of things along the radial line. And the sort of connection in the radial direction behaves actually as a connection, so you can compute little chunks of parallel transports there, little holonomies along the radial direction, whereas the transverse variables behave like scalar fields, so you treat them using point holonomies, okay? So this looks like a holonomy, but you realize there's no integral because it's a point holonomy. And graphically, this would be sort of holonomies along this direction labeled by numbers, just like in ordinary spin networks, whereas in the transverse direction, you have insertions that are labeled by real numbers. Now, when you try to do spherical symmetric gravity, you have two constraints. You have the diffeomorphism constraint in the radial direction, and you have the Hamiltonian constraint. And just like in the full theory, these satisfy not a Lie algebra, but an algebra with structure functions. So that is a problem, because we don't know how to deal with that. Now, it turns out that we discovered that in the case of spherical symmetry, you can do a combination of the constraints, of the diffeomorphism and Hamiltonian constraints, in such a way that the resulting algebra is a Lie algebra, and therefore you can proceed forward with a Dirac quantization. It's not entirely clear why this happens for these models, but it does happen. And it's not entirely clear for what other models such a thing could happen. So as a consequence of that, we were able to find a basis of physical states labeled by the graph, the labels of the spin network, and the ADM mass. And remarkably, we were able to find in closed form the solution of the Hamiltonian constraint. So this constitutes a basis of physical states for pure gravity. And you can choose states that approximate the Schwarzschild solution very well in the regions of low curvature. But if you go into the black hole, into the regions where the curvature is large, you'll find a region where space-time is not well approximated by a classical geometry, but it's still, the theory is still well defined, and you can go through it and eliminate the singularity. So what we're going to do is we're going to take that quantum space-time that we have now, that doesn't have a singularity anymore, and we're going to put quantum fields to live on this quantum state. And we're not going to study back reaction. We'll just let the quantum fields live there. So as a consequence, it's okay to take as an approximation that the states have the form of a direct product between gravity and the matter states. And we'll represent the matter part of the Hamiltonian as a direct observable acting on the quantum geometry, and take an expectation value of it and proceed to do a Fock quantization of the quantum fields. So we'll have a full loop quantum gravity treatment of the background and a Fock quantization of the fields living on it as a first approximation. So this is what we mean by quantum field theory on a quantum spacetime. So the Hamiltonian of a scalar field takes this form, and if you squint your eyes, you'll see there's a p phi squared as usual, the scalar field derivative as usual squared, and a linear term in the space derivative because we're in spherical symmetry, and the coefficients are functions that operate on the quantum geometry, and they're completely well defined. I mean, they look complicated, but this is all numbers acting on the states of the quantum geometry. So it's completely straightforward to take the expectation value of this Hamiltonian constraints. And it's completely straightforward to work out the equations of motion of the resulting expectation value of the constraint you get. And the equations of motion just become essentially a wave equation on a discretized lattice spacetime. So a couple of observations have to be made. The lattice spacing here of the quantum spacetime, which is given by the sort of vertices of the quantum geometry, is not arbitrary, but it's bounded by the condition of the quantization of the area. So the spacing has to be at least Planck length squared divided by 4 times the mass of the black hole. Notice that this could be potentially considerably smaller than a Planck length square. So the spacing can be, if you want, if you choose your quantum space to be it, very, very fine. And therefore, the approximation of having a sort of discrete spacetime approximates the continuum very well. There you can just proceed as normal in quantum field theory in curved spacetime to define the modes for scalar fields living on this quantum geometry. And you can define the Unruh, Bulwer, and Hartle-Hawking vacua. The main thing that changes is that the dispersion relation that you have, no matter how well you approximate your continuum equations with your discrete treatment, the dispersion relation is not that of the continuum anymore, but it's a dispersion relation of the lattice. As a consequence of that, trans-Planckian modes are suppressed. And this leads to many calculations of quantum field theory in curved spacetime, like for instance the expectation value of the stress energy tensor to be finite. And this might have implications in the future for back reaction calculations, but as I mentioned, we're not looking into that right now. So out of that horrible looking, apparently Hamiltonian that we had, if you sort of work out the equations of motion, it turns out that at the end of the day you end up with an ordinary wave equation with small corrections. So for instance, if you look at the Bulwer case, this is the form of the wave equation. And if you squint your eyes, you see a wave equation there, d time second, d spatial second here, but with some details that this lattice spacing is sort of point dependent and so on and so forth. And so this is messy. I mean, if you want to treat this, you'll have to put it on a computer, okay? And we don't want to do that because, as I said before, outside the black hole, we are approximating with an excellent approximation the continuum. So all these details of the different spacings and so on should go away. And indeed, if you look far away from the black hole, the spacing becomes uniform, and the modes become the usual modes of quantum field theory in curved spacetime. The only difference is the dispersion relation, again, as I mentioned, is that of the lattice. And you can do similar analysis for the Unruh and Hartle-Hawking vacuum. It's a little bit harder because the slicing in those cases imply that your spin network will be moving with time. There's nothing wrong with that. You can do the whole thing, but it's a little bit more complicated, so I won't list it here. So since we have all this, can you do things like study Hawking radiation on these quantum spacetimes? And the answer is yes. So to study Hawking radiation, of course, what you want to do is you want to compute Bogoliubov coefficients. And you do that with the ordinary modes, in this case in spherical symmetry. And the calculation goes through exactly like it does in traditional treatments. So we can just borrow any paper on Hawking radiation and copy almost all the formulas until you reach a crucial one in which you are computing the expectation value of your number operator on the out modes on the states of the in modes. That's what gives something non-trivial here. And you have a bunch of form factors as usual. And this is the traditional calculation. As you notice here, there's a regulating factor because this integral blows up at z equals 0. There is where our calculation slightly diverges from this because we are in a discrete situation, and therefore that point is omitted from the calculation, and it becomes finite. And it turns out that we don't have to do any calculation to do this, because this had all been considered before by the Milwaukee group when Ivan Agujo was a postdoc there. They had not considered loop quantum gravity for the Hawking radiation. What they had done is they had posited the question, what happens if quantum gravity imposes a cutoff on things? How does the Hawking calculation change? Okay? And it turns out that they had discovered that it's rather tricky because depending on how you impose your cutoffs due to quantum gravity, it could screw up your Hawking radiation calculation badly. And what we discovered, to our surprise, because we weren't aware of this result when we started doing this calculation, is that this discretization that loop quantum gravity imposes is one of the good ones, one of the ones that doesn't screw up the Hawking radiation. And from there on, we could copy everything in their paper and reach a final result that gives you the traditional formula for the Hawking radiation, plus a small correction due to sort of Planck effects. Now, again, you might say, well, but I mean, we expected this, right? I mean, outside the black hole, there's nothing new in your treatment. The corrections are very small. Hawking radiation is exterior. This should work. But again, as these people pointed out, it's not that simple when you introduce a cutoff. Even if you're in the exterior and things are sort of smooth, you can screw up things. And it's sort of remarkable that naturally, loop quantum gravity leads you not to encounter that problem. The next thing we looked into was the Casimir effect. This arose because I was giving this talk in front of a sort of mixed audience. There were condensed matter physicists, and they asked me, well, yeah, all this is very nice, but can you compute something that we can measure? And my response initially was, well, you know, quantum field theory in a fixed background, free field theory, there's not much you can predict that you can measure there. And they said, yeah, you can compute the Casimir effect. And so, well, we decided to compute it as a consequence. And so we want to do the Casimir effect on these quantum spacetimes, and they're spherically symmetric, okay? So the Casimir effect, as you know, it comes from putting a quantum field theory in a box. Since we're in spherical symmetry, our box has to be spherically symmetric. So we take sort of two shells, spherical shells, and try to study the quantum field in between them. And so what we need to do then is to compute the energy of the quantum field computed between two shells and see how it changes when you move the shells. And that gives you the Casimir force, presumably. Okay, so we need to compute the stress energy tensor. And we need to do it for modes that are spherical, but also that are sort of zero on the two shells. So you have to impose Dirichlet boundary conditions on the shells. And this is a problem in your first course in electromagnetism, how to write spherical waves that vanish on the two shells. And you can just write it down. And with that, you want to compute the modes for your field. And you want to compute the expectation value of the various components that appear on the stress energy tensor, which in these type of calculations are not done with this trick, considering the Green's function and so on and so forth. This is fairly standard. And the other problem you're facing, of course, is a stupid problem, but it is a problem, which is that in spherical symmetry, the modes of a scalar field are not known in closed form. Okay, so that screws up any analytic calculation you want to do, so you should try to do it numerically or so on. To avoid doing that, we're going to assume that this whole experiment with the two shells is really far away from the black hole. And we're going to enclose it in two other shells. So it's a box within a box, and we put the whole box far away. That prevents us from having to compute the modes all the way back to the horizon. We just have to compute it to our box. And also to infinity. That's not a problem. We can do that, but just putting a box there makes the calculation clean. And we compute the energy of this whole thing. And so the energy will be the integral from here to here of the stress energy tensor, the integral from here to here of the stress energy tensor, and the integral from there to there of the stress energy tensor. And the remarkable thing is all this thing now is finite, because we're on a lattice. I mean, it's a very fine lattice, but it's on a lattice, so nothing diverges anymore. So this is what I was saying before. Normally, the calculations of the expectation value of the density blow up. In this case, they don't, because we're in a discrete space-time. And so this whole thing is finite. You can compute it. You take the derivative with respect to this separation there to see how it changes, and you get the Casimir force. And remarkably, you get the correct result, with corrections, of course, because it's all approximate in the lattice. And the remarkable thing is we didn't have to either regularize nor renormalize to do the calculation, which normally you have to do. And the reason we didn't have to do anything is because the background quantum space-time regulates things. So this is, in my opinion, incredibly clean calculation, because we just computed the energy, took the derivative, and got the force without regularization and without renormalization. So this, in a sense, is bearing out the promise that for many years people have said that sort of quantum gravity will become the regulator of matter fields. Now, before you get too carried away with this, there's a caveat here. Yes, these quantities are all finite, but they're all very large because, okay, the cutoff imposed is Planck's scale. Okay, so the energies of these fields, although they're finite, are very large. Because we were interested in the Casimir effect that depends on differences of energies. It doesn't care the calculation that the energies are large. It only cares about the differences, and the differences come out correctly. But if you're interested in other effects, like back reaction, for instance, of this thing, you're going to have to do something about it, some sort of finite renormalization, because the energies are clearly wrong. It's remarkable that the energies are clearly wrong in the sense that they're very large, but their differences come out to be correct to give the sort of Casimir effect. We extended this whole treatment beyond vacuum to the case of self-gravitating shells. Okay, that's the next step, if you want, in spherical symmetry. So the Hamiltonian is pretty much the same we had before, but there are all these terms with deltas and thetas and so on having to do with the shell. Now, there are new Dirac observables associated with the presence of the shell, of course. And through a lengthy calculation, we showed that, again, the algebra could be turned into a Lie algebra. So you could try to do a quantization. But unlike before, we do not know how to find the physical space of states in closed form, which is sort of reasonable, right? Because there's a huge gap between just doing sort of the eternal Schwarzschild black hole that is sitting there forever and trying to study the collapse of a shell. Because even though the shell is relatively simple, the collapse of a shell produces a black hole, it's dynamical, and so on and so forth. And therefore, it's not expected that as a quantum sort of treatment, this should be easy. So we do not know how to do this in closed form. So, however, motivated by this, we decided to do a further approximation. So what we did is to keep in the calculation a couple of the effects that the quantum theory brings in, namely that the position from Scri, where you throw in the shell, and the ADM mass are canonically conjugated variables. And then we throw away all the other elements of loop quantum gravity. We don't have discrete space-time anymore and so on. We just keep the canonical treatment in the sense that those two variables are canonically conjugate and try to treat the Hawking radiation of a shell on that quantum space-time with that little only element of the two canonically conjugated variables and try to analyze how does that influence the Hawking radiation. So what we're going to do is we're going to treat the Hawking radiation in the so-called geometric optics approximation. What is this thing? Well, you have a shell, right, that collapses and forms a black hole. Space-time is written there, meaning a Schwarzschild up here, flat space-time down here. And the geometric optic approximation says if I throw in a light ray from here, it bounces and it comes back, and like that. And there's a limit ray, of course. If I bounce like that, I come in the horizon, and anything beyond that will fall into the black hole. The geometric optic approximation consists in a formula that connects this value with that value up there, and this allows us to relate the in modes down here in Scri minus with the out modes up there in Scri plus. So the modes are written there in terms of V here, in terms of U there, and the relationship between V and U is given by this little formula here that is given by this geometric construction there. Once you have the modes related in that way in the same variable, you can proceed to compute the Bogoliubov coefficient. And this goes all the way back to Hawking in 1975. That's the way he did the calculation. So the new thing we bring in, so this is the traditional result for the Hawking radiation. The new thing we bring in is that the anion mass of the space-time and the position at Scri, where you throw in the shell, are canonically conjugated variables. So we're going to promote them to quantum operators operating on a quantum space-time. For instance, wave functions of the mass of the space-time. And then the quantum time of arrival formula that we had here becomes an operator relation acting on this quantum geometry. The Bogoliubov coefficient, therefore, becomes, what normally are numbers, become operators operating on the quantum geometry. And there's some details there because, of course, the domain here is not the full Scri because some of the light rays that fall in never make it out and so on. So you need to be a little bit aware of that, but that has standard and people have thought about that. So there are ways of analytically extending this expression so it's correctly behaved. And so at the end of the day, we can compute the expectation value of the number operator by taking the Bogoliubov coefficients and taking the expectation value on the quantum geometry. So if you consider a squeeze state that is centered about a mass for the collapsing spacetime, you get an expression here that is not terribly transparent. And if you take the classical limit, you get the traditional factor for a classical shell with a correcting factor in front. The interesting thing is that there appear non-trivial correlations between different frequencies. So if you take the expectation value of the number operator for two different frequencies, normally in the traditional calculation that Hawking would have done in 1975 on a classical spacetime, these correlations are zero. Whereas if you consider them in the quantum spacetime that we're considering, these correlations are non-zero. The message is the Hawking radiation becomes non-thermal due to the fluctuations of the quantum spacetime. That opens the possibility for information to leak out on the radiation. So the next question you might have, therefore, is does the whole information leak out or not? Well, unfortunately, this example is just too simple, okay? The only information we have is the quantum state of the initial shell that we took to be a Gaussian. So if you take the sort of semi-classical limit, what you find out is that the expression that you get is the traditional Hawking radiation plus a term that is the Fourier transform of the Gaussian. So it has the whole information of the quantum state. So the first thing is to get excited and to say, oh, we're recovering all the information of the quantum state in these non-trivial correlations of the radiation that comes out. But again, you have to be a little bit careful because the example is so simple, the information coded in the initial state is rather limited, and therefore the fact that you can get it out is not necessarily proof that in a realistic collapse situation, you'll be able to get out everything from this. And there's further discussion of this here. To conclude, let me give you a bonus. We're moving beyond spherical symmetry into axial symmetry. So we now want to consider spacetimes that depend on two non-trivial coordinates and, say, one coordinate that has a killing vector around, so we have axial symmetry. There's a little stumbling block, and it's the fact that when you have sort of variables that have internal degrees of freedom, you don't have to demand that the killing vectors just drag them into zero. It's a possibility that the dragging of your variables produces an internal gauge transformation. And it turns out that if you set this to zero and just say, oh, my variables are killed by my killing vectors, is wrong. I mean, you don't capture all the degrees of freedom of the problem. So the first sort of stumbling block is kind of technical, but we needed to determine what kind of internal gauge transformation was needed to capture everything we needed from this problem. And we determined that if it was an O1 transformation, that was enough. This discussion, of course, goes way into the past. I mean, these people considered already this problem in Yang-Mills theory and noticed this, but for every problem you have to re-examine it again. In fact, with Vikar Hussain a gazillion years ago, we wrote a paper where we completely ignore this fact. And at the time, of course, there was no Ashtekar-Lewandowski measure, there was no Thiemann-Hamiltonian, so you could make very little progress. So we were oblivious to this whole thing. We sort of advanced for a while and stuck. But if we had been able to progress further, we would have realized that our choice with this equal to 0 was insufficient. In the end, this leads to variables that depend on just reduced variables that live on the sort of r theta plane. And in terms of that, you can encode everything in your problem. And we have showed that in this treatment, we can accommodate the Kerr solution well. We have studied the boundary terms that are needed to make everything differentiable at infinity. And so what's next then? The next would be to try to build a quantum theory. So the idea would be, in terms of the reduced variables in the r theta plane, you would build traditional holonomies, the loops that live in the r theta plane. You have to be a little bit careful because, of course, the r theta plane is not infinity to infinity. It's a finite domain. But these will behave like ordinary spin networks, just in 2 dimensions. And you have point holonomies for the third variable sort of inserting, pretty much like we have in spherical symmetry. And we did a preliminary analysis of this shows that the Hamiltonian constraint looks pretty much like Thomas's Hamiltonian constraint. This, by the way, is a departure from spherical symmetry. In spherical symmetry, because you don't have those sort of exceptional vertices that Thomas uses to make his constraint close, we had to do something different for the Hamiltonian constraint. Whereas here, you can implement the Thiemann constraint just like he does in 3+1, but in 1 dimension less. And what I find interesting of this is, as you know, over the last few years, Madhavan has been experimenting with new Hamiltonian constraints, a little bit more detailed and complicated than Thomas's one. And the construction is fairly elaborate and complicated. And by dropping 1 dimension, this would be the simplest context in which these constructions can be probed, and hopefully progress will be made. And so this, of course, will be continued in the future. So let me conclude here. So we showed we can solve loop quantum gravity with spherical symmetry in closed form. We can put to live quantum fields on these quantum spacetimes. Just like Jurek did in cosmology, we do now in spherical symmetry. Quantum field theory in Kerr spacetimes is approximated very well. The discreteness regularizes physical quantities, and so this opens the possibility of back reaction calculations. We haven't done those yet. The Hawking radiation can be computed, and the result is it coincides with previous heuristic results where people had introduced a discreteness ad hoc, but now with the discreteness introduced just by loop quantum gravity. We were able to study self-gravitating shells, and geometric optic calculations on self-gravitating shells suggest that information may leak through the Hawking radiation, and we're generalizing this to axisymmetry, and there's a new arena to test the dynamics of loop quantum gravity with 1 dimension less. Hopefully that will lead to simplification and to further progress. Thank you very much.
Thank you very much. We have some time for questions. I see Carlos' hand.
Thank you, Jorge. This was very nice. I found very nice the fact that the Hawking radiation calculation, which somehow finally confirms this old idea that this very nicely. I mean, Jacobson and company already had suggestions that Hawking radiation has nothing to do with deep ultraviolet. And here, loop quantum gravity is coming strongly on that very clearly. But what I was particularly intrigued is your treatment in this. One of the last things you did with this optical ray approximation, you use the mass of the whole as a variable, right? You have if I get it right, you only use it for then computing the expectation values of Bogoliubov coefficients in a state of this of the right. But here, there's one thing that it's open, which is the fact that the organization has a back reaction on the mass, which of course is not seen by this calculation. Which means that some information could also go into the quantum spread of m at infinity. So this seems to open that.
Yes, absolutely. I mean, we haven't done that, but it's obvious that it should be there. Yeah.
So in your calculation of the Casimir force and the Casimir energy, would it be possible to get the same correct result, but at the same time not have these large terms if you were to use a normal ordered energy momentum tensor operator? Could that possibly solve that problem?
Yeah, but as you know, normal ordering is not well defined in general, so we didn't want to do that. I mean, we want to pretend that we're in the sort of generic situation where you don't know what to do with normal ordering, and then you would be led to this, right? Yeah, sure.
Could I continue on that question? So in this Casimir energy calculation, could you comment on the specific role that the gravity input plays in the calculation? I mean, I could say that I'm in flat space and I could introduce a lattice by hand and so on. Could you compare what role gravity has for you?
I'd say that at this level of the calculation, where we're doing it very far away from the black hole, you're essentially in flat space with a lattice. And the role of gravity is to determine the background quantum state, which determines the lattice. And there's not much input from gravity into it. Perhaps the only input you have is that the lattice spacing cannot be smaller than a certain amount given by the area sort of condition.
Yes.
So actually I have a question about this lattice spacing. So this is what produces the modified dispersion relation I get. And the question is, where does it come from? Is it just the length or kind of the area associated to the...
Well, if you want at the very basic level, is that you don't have wavelengths smaller than the lattice spacing. And that is enforced by this dispersion relation. That
so basically your linear spin network,
right.
It's not diffie invariant.
Right.
It has a physical
spacing,
length.
Yeah.
I see. Okay.
I saw a hand here. Yes, Jurek.
Could you elaborate more on this difference which quantum gravity makes for the Hawking radiation?
Yeah, so there's a cutoff that's introduced. That's the main thing. Plus small little corrections, because of course the space-time is not exactly Schwarzschild, it's little quantum Planck length corrections. Those aren't terribly interesting because they're very small. But the fact that you introduce a cutoff, and nevertheless the cutoff doesn't mess up the Hawking radiation, is, I think, what is kind of surprising of this calculation.
Could you show us again this formula for
Yeah.
expectation value to ends?
It's here. Yeah, so this is standard formula for the expectation value of the number operator on the vacuum. So you take the in vacuum, you take the out n operator, and that gives non-zero normally. And there's a bunch of gray body factors, and there's this term here that blows up when z equals 0. And the thing is, when this becomes discretized, this sort of doesn't blow up anymore, so to speak.
And this shell which here produces the space-time, it is classical.
This is on just Schwarzschild.
Oh, this was
This is Schwarzschild. If you do it on the shell, you get a similar result, but this is for Schwarzschild.
right, but in that case, did this shell bounce?
No, I mean, this whole thing, this whole integral is a sort of scry. So in the space of a shell, this whole integral is up there. So it only cares about this portion of the space-time, which is exactly Schwarzschild. So the calculation goes the same way in both cases, basically.
Maybe one more question, if there is one. If not, thank you very much again.